This is sample 9-7, Drama in the Skies. We've got two birds that are going to collide. The first is a hawk, which I'm going to call M1, 600 grams. He's flying at a speed of 12 meters per second, and they say he's traveling 30 degrees below the horizontal. So the book sort of has him going to the left, but I'm going to have him going down 30 degrees below this horizontal. All right, our second contender here is the pigeon with the same mass of 600 grams. This guy has a velocity of 8 meters per second, and he's traveling horizontally. So here's my pigeon here. All right, now the birds are going to stick together and move as one after the collision. So this is a perfectly inelastic collision. And you can guess from the drawing that the final velocity is going to be in quadrant 4 because nothing else really makes sense. Okay, they're actually going to ask us what is the final velocity. So we can do this using vector component strategies here. So if we write our conservation of momentum in the x direction, we have the initial momentum of the hawk is m1 times v1I, and then we need to take the x component, so that's cosine of minus 30 degrees. The x component of the pigeon is m2 v2I. The pigeon's only moving in the x direction. If you wanted to write here cosine of 0 degrees, you certainly could, but guess what? You're going to get 1, and we're going to reduce that down to m2 v2I. Right, what's that equal to? Well, that's equal to the x component of the final momentum of the pigeon-hawk combination. Here's the mass, and here's the x component of the final velocity. We're going to do the same thing in the y direction. We've got m1 v1I for the hawk, and now we need to use the sine of that, negative 30 degrees. And this term is 0, okay, but we'll write it out just in case we wanted to, v2I, and we have the sine of 0 degrees, which is, you guessed it, 0. So that's equal to m1 plus m2 times the y component of the final velocity. It turns out we have all of this data. We have all the m's and we have all the vi's, so, and we have the thetas. So we can solve flat out for vfx, which equals 9.2 meters per second. That's positive. VFY is minus 3.00 meters per second. That's negative. This gives us a fourth quadrant vector, kind of exactly like I predicted back here. And then to find VF, you just use the Pythagorean theorem, 9.2 squared plus 3 squared. Take the square root, and we get 9.7 meters per second. Remember, to find theta, we use the inverse tangent of the y component over the x component, and that gives you negative 18.1 degrees. Now, I don't like the negative degrees, as you know, if you've been paying attention. I would just say 18.1 degrees below the horizontal. That's how they started, with below the horizontal, so that's, you can just write below. I'm running out of room here, but below horizontal. So 9.7 meters per second, 18.1 degrees below the horizontal, which makes sense as far as our prediction goes. So that's our last sample for section 2.